In physics, two-dimensional motion also refers to a category of motion we call relative motion. To explain this concept, we'll use a simple example called row your boat. In our example, let us envision that we are in a rowboat and attempting to row across a river. In our diagram, we show where X marks the spot. That is our final destination. So, we get in the boat and we begin rowing straight across the river with a certain velocity of the boat at v sub b in meters per second. At the same time, we are attempting to row across the river. The river is flowing, in this case, to the right, with a velocity of v sub r meters per second. That is, the water is flowing in that direction with that velocity. That would mean that instead of landing directly across from where we started, we would be pushed downriver to a new landing spot as indicated in the diagram. That means, once again, we can describe our motion with a triangle, where we have a velocity in the x direction equals v sub I cosine theta, when we define the x direction as the direction that the river is flowing. We could then define our y direction as v sub I y, and the y direction when we describe y as being the direction you are rowing. Our total velocity is the hypotenuse, which incorporates both the velocity of our boat across the river and the velocity of the river flowing. This diagram shows how the two triangles are similar, and in fact, it shows we can also determine where we will land as we cross the river. This requires some additional steps. Let's start with saying that we know the distance across the river. In our frame of reference as drawn, we would call that delta y. That means we can determine the time it will take us to cross the river by looking at delta t equals distance across the river, delta y, divided by the velocity of the boat that we are rowing straight across the river. That would mean we could also figure delta x, or how far downriver we had drifted with the current, by taking that amount of time available as we row across the river, delta t, and multiplying it by the velocity of the river. So, as the diagram shows, not only would we cross the river, but we would also go a certain displacement, delta x, down the river. As you can see, the total distance, or displacement, that we want would be described as the hypotenuse of our triangle, looking at delta x and delta y as distance downriver and across river, and our angle theta would be the angle of our displacement. In other words, we could take that angle and determine where we would end up across the river downstream. Now, let's say our destination lies directly across from us, across the river, at a 90-degree angle to the riverbank, i.e., we want to go directly across the river. From our previous example in this presentation, we know that the river will push us downriver, and that in the amount of time it takes us to get across the river, we will be pushed downriver at the velocity that the river is flowing. We know that we can determine a delta y and a delta x and an angle of our determinant or resultant motion as we go down the river. If we want to arrive straight across the river, then we would have to use that information and create a mirror image, if you will, and use that same angle and point our boat upriver at that theta, so that by the time we cross the river, it will have pushed us down to our landing point. You will see problems like this in relative motion, particularly in some of the examples that we have, and it will make you determine the angle that you would need to launch to ensure that you landed at your destination. Okay, feel free to refer to this presentation at any time to refresh. Also, feel free to refer to the triangle math presentations so that you can use sine, cosine, and tangent as needed.